Right, our last example today will be just an example of the Hessian. Remember, we'll be talking more about all of this stuff, the Hessian, the gradient, tangent planes, partial derivatives in a future chapter. We're just sort of building the machinery right now. So I want to find Hessians of both f of x equals x squared plus y squared and g of x is x squared minus y squared. So let's do both of these. For x squared, so f of xy is equal to x squared plus y squared. If I want to know what fxx is and what fyy is and what fxy and what fyx are, I first have to find fx. So a first partial with respect to x is 2x. A second partial with respect to x is 2. A first partial with respect to y is 2y. A second partial with respect to y is equal to 2. And if I look at their mixed partials, fxy, that's a derivative of 2x with respect to y, that's going to be 0. And fyx is equal to 0. And so in this case, the Hessian of f, which is fxx fyy minus fxy squared, is exactly equal to 2 times 2, which is 4. Actually, this is enough information to conclude that I am concave up at this point. And if you look at a graph of this thing, of course, to be clear, it's not obvious that it's enough. We have not learned this yet. But if you look at a graph of this thing, x squared, y squared is a paraboloid, and this is actually a local min. It is actually concave up there. And it turns out that what we've done is actually enough to show that. But that's for future a future endeavor for us. What about gxy equals x squared minus y squared? So here fx is going to be 2x again, but fy is equal to negative 2y. Fxx is going to be 2. Fyy in this case is negative 2. And again, fxy, which is equal to fyx, so we really only have to compute one of these, is 0. And so here the Hessian of f is equal to, again, fxx times fyy minus fxy squared. And in this case, it's equal to 2 times negative 2 minus 0, and that's negative 4. And we have actually talked enough about the fact that if it's negative 4, that means that fxx and fyy have different sign. So I'm concave up in one direction and concave down in the other direction. And so actually, if you graph this thing, that's exactly what's going on here. I am concave up in the x direction, and I'm concave down in the y direction. So again, this is a very hard thing to draw, drawing saddle points. When I was your age, when I was taking multivariable calculus, there wasn't anything like GeoGebra for me to graph on. So I would encourage you to GeoGebra with both of these. So use GeoGebra to graph both of these, and show yourself that this is concave up, and that the other one is a saddle point. Again, we're defining saddle point, we're defining concavity in a future slide, in a future lecture, but I just think it's interesting to sort of have a sneak peek here.